All right, here we go, section 10.7, factoring special products. All right, so special products or special factoring patterns that we can use here are the difference of two squares or the perfect square trinomials, which goes back to when we were multiplying binomials and we could do a sum and difference or square a binomial. So we're just doing the reverse of those two operations. So difference of two squares says that if I have something that's in the form of a squared minus b squared, two things that are perfect squares separated by a subtraction, I can figure out what the square root of each one of those is, and it becomes a plus b times a minus b. The square root of this term plus the square root of that term, and the square root of this term minus the square root of that term. So if you just have two terms separated by a subtraction, check to see if they're both perfect squares. Perfect square trinomial is going to be a trinomial. So the first term and the last term, a squared and b squared, are perfect squares. So if the first term and the last term are perfect squares, then we check to see if the middle term is 2 times the square roots of those two, the first and last term. And then we can factor it as a minus b squared or a plus b squared, depending on what our symbol order is, right? If it's minus plus, it's a minus b squared. If it's plus plus, it's a plus b squared. So factoring, m squared minus 9, two terms separated by subtraction. So do they both have a square root? Of course, m squared, the square root of that's going to be m. 9, the square root of that, hopefully we know, is 3. So those two terms are perfect squares. Right? Or this is just like having m squared minus 3 squared, which fits our a squared minus b squared format. So when we factor that, it's going to be first term plus the last term, m plus 3, and m minus 3. B, 49q squared minus 81, two terms separated by subtraction. So 49q squared is our first term. Does it have a square root? And 81 is our last term. Does it have a square root? 49 is 7 times 7. So 49 has a square root. Q squared is just going to become q. 81, hopefully remember our math facts and know that 9 times 9 equals 81. So it has a perfect square root of 9. So we can write this as 7q plus 9, 7q minus 9. All right. C, we have 12 minus 27x squared, and 12, if we take the square root of that, that's not a perfect square. 27 does not have a perfect square. All right. 5 times 5 gives us 25, but 6 times 6 gives us 36, so it's somewhere between 5 and 6. All right, 12, 3 times 3 is 9, 4 times 4 is 16, so 12 is somewhere between 3 and 4. But one thing we can look at, if it doesn't fit the pattern, we can see if there's a term that we can divide out of both of those, which 12 and 27 both would divide by 3, which would allow us to bring a 3 out of there. And 12 divided by 3 is 4. 27 divided by 3 is 9. So now we have 3 times 4 minus 9x squared. Which now if we look at what's left, if we take the square root of 4, that's 2. 9x squared, take the square root of that, that's 3x. So the two terms we have left here after we pull the 3 out actually do fit a squared minus b squared, or the difference of two squares. So we could write that, first start with the 3 that we pulled out to begin with. and then 2 plus 3x, 2 minus 3x. And there's our factored form. All right, so those were all difference of two squares. And now we're going to look at this next group, which are going to deal with perfect square trinomials. And one thing I need to rectify is I left off having a plus plus example, so I changed a to x squared plus 8x plus 16. So on your notes that you printed off, if you printed off the notes, it's going to be x squared minus 8x plus 16. So just change that first subtraction into an addition so you can follow along. All right, so check the first term and last term, see if they are perfect squares. X squared, you can take the square root of that, and that gives us x. 16, which is the last term, square root of 16, 4 times 4 equals 16, so that's 4. So those are perfect squares. Then we check to see the middle term. Is that 2 times the a term, which is x, times the b term, which is 4. So 2 times x times 4 is 8x, which matches up with the middle term there. So this fits into a squared plus 2ab plus b squared, which means we can write it as the a term x plus the b term 4 squared. Next one, 9y squared minus 60y plus 100. 9y squared, if we take the square root, 9 is 3 times 3. Of course, y squared is y times y, so 3y. 100, the last term, does it have a square root? It does, which is 10. Check the middle term, is that 2 times 3y times 10? So basically these two multiplied together times 2, which would be 60y, which matches up. So, and it's minus plus, so we're in the a squared minus 2ab plus b squared format. So that's going to factor to the a term, which is 3y, and it's minus this time 10, and it's squared. All right, C, 2x squared minus 12x plus 18. Check our first term, not a perfect square. 2 doesn't have a square root. Last term, 18, it doesn't have a square root. But if we look, 2, 12, and 18, all of those numbers will divide by 2, right? So I can pull a 2 out to begin with. And 2x squared divided by the 2, it's going to be x squared. 12 divided by 2, it gives us minus 6x. And 18 divided by 2 plus 9. Now if we look at those, x squared has a square root, which is x. The last term, 9, has a square root, which is 3. And if I do 2 times x times 3, that equals 6x, which is what we have there. So it fits the a squared minus 2ab plus b squared format, or we're going to become a minus b squared. So before we do that, don't forget that we pulled out a 2, so we need that to be at the beginning. And it's going to be x minus 3 inside the binomial squared. So 2 times x minus 3 squared. And that is factoring using special patterns, section 10.7.